All right, hello everybody. We are Cowboys Stormwater Management. My name is Zach Bradley.
I'm Riley Jones.
I'm Grant Moore. And I'm Derek West.
And we've been tasked with dealing with the stormwater management issues at Parkview Estates. I will ask everyone to hold their questions till the very end of the presentation. So just when we got started, we wanted to come up with a mission, kind of a direction for us as a group. So our mission statement we came up with was that Cowboys Stormwater Management team was to design and implement sustainable storm and surface water systems that control erosion damage from stormwater runoff, improve urban development, and enhance quality of life in Stillwater, Oklahoma. Just a quick overview of our project. Our client was the Parkview Estates Homeowners Association. Parkview Estates itself was established in 1976. The Homeowners Association was established the next year in 1977, and they currently preside over 230 homes. Our period of performance was, obviously, we started in the fall semester. We started with 3 meetings with the Homeowners Association. What they really wanted from us was a delivery of cost-based solutions, kind of broken up for each problem area. And then during the spring, we met with them at the beginning of the semester to narrow down on the solutions, find one, and kind of move forward with that solution for each site. That being said, from those meetings, we came up with a few requirements from them. They wanted to eliminate the ponding in their streets and yards. They wanted to reduce erosion in both the public areas and along the stream banks of the stream in their green space. And then they wanted us in the fall to provide them with 3 cost-based solution options. From these requirements, we came up with a few constraints. Obviously, feasible cost-benefit ratio is a big one. You want to get as much bang for your buck out of your design. Of course, safe was huge. They wanted it to be naturally aesthetic and have a long lifespan. And then with that, they also wanted us to be able to come back in and potentially be able to add stuff in the future. They wanted to be able to kind of tack on to this current design later on where some more money might be available. And then, of course, budget is always a big constraint.
So just a little quick project review. This is an image, an aerial image from Google Earth. You see at the top, this is our problem site A. It is at the cul-de-sac of Marie Street, or Marie Drive. This is our problem site C. It's the entire ephemeral stream that runs through the Greenbelt area. And by ephemeral, I mean it only fills up during storm events. So there may be water like in the stream, but there's no flow. And here is our problem site C. After speaking with the Homeowners Association, we decided to go with the low-cost solution. And so our low-cost solution for this problem site C was just to do nothing and leave it alone. We'll get into that a little bit later, but for our project, for site A, here at the East Murray Drive, there's a swale, a grass-lined swale, as you can see from the image next to it. Whenever storm events happen, it becomes really flooded, and due to the grading of the swale after the inlet, the water gets stuck there. Moving on to site B, it's from top to bottom, it's 1,700 feet long. As I just said, it's an ephemeral stream, and there's 3 major inlets to the stream, and they come in from site C right here. They come through site A to here, and then this cul-de-sac also inlets into the ephemeral stream. This is just some of the main problems we see at problem site C, or at site B. This is a giant hole just kind of right towards about 300 feet from the bottom of the top. But it's constantly full of water, and as you can see on the right image, it's starting to cause a pretty large problem. Here's the area at site C. It's already got riprap on it, and other than small rocks being taken away, it's still in really good shape, so we didn't want to damage the structure and the rooting system that was already there. So we just decided to leave it as is. Just for a third-party involvement, Parkview Estates asked us to see if there's any way that we could get the City of Stillwater to help out with some of the cost sharing. And this is a manhole that is just to the left of the Site C outlet. And as you can see, the ephemeral stream is starting to erode around it, so we would like to be able to get something done there and hope that the city of Stillwater could help with that. And as far as for sources of the flooding, this is an image of the original site plan of Parkview Estates. It was designed in the early 70s. And as you can see from the quadrants, they designed this neighborhood in pieces. So as for like problem site C, it was made in the zone 2, and everything, it was designed for that flood, for that type of drainage situation. And so everything that's been built above it over the last 50 years is going through that same drainage system, and that's why we're seeing a lot of flooding occur. There's also a problem in Site B. It's basically a barren stream. There's not really a lot of vegetative cover, which is why the sheet erosion is happening and the cutting at the problem Site B that you just saw. Also, the soil type of the neighborhood is a major concern. They're just mostly clay, and after soil testing, waited for a couple hours and it didn't drop at all, the levels. And for our watershed delineation, we decided to use stream stats. And we did that so we could find the contributing area of the watershed to our outlet at Site B. And after that, we decided to do ground proofing to make sure that our data was, the data we collected was correct. And so that image in the middle is what our final product of our contributing watershed was. And to the right of that is our Google Earth we made sub-reaches using Google Earth Pro, and we used the sub-areas to determine individual areas for water flow.
Okay, here's some more background and research. To determine the cross sections of the stream and the Site A, we use laser levels and measuring rods and 300-meter tape. What we would do is lay the tapes out and get points along a perpendicular cross section of the stream, probably around 5 feet each. That gives us a nice view of what that individual cross section looks like. This data helps in the design of Site A and Site B. When determining the soil, we used a ribbon method. This is a method by the NRCS, Natural Resource Conservation Service, formerly known as the Soil Conservation Service. This method is a touch and observation feel method that you take the soil, rub it in your fingers, as you can see on the right, until it makes a ribbon. And then once that ribbon breaks, you can measure it, and that will tell you a soil type. You can do the feel is by rubbing the soil in your hand, and by a level of grittiness, that will give you a soil texture. These methods were used to determine the soil types and texture. As you can see in this last picture, we took a soil probe and we got about almost a foot of clay at the topsoil. So some more background and research. At the beginning, we were trying to implement low impact development by use of a bioretention cell, rainwater harvesting at individual houses, and permeable fields and some of the culverts. Due to some budgets and feasibility of it, we decided not to go with the low impact development, but more simple designs. And we will get to that later in the future expansions.
Okay, so now we're going to start talking about what our final designs are for our project. And so we're going to start with problem site A. Now there are two main problems at this location, the first of which being the ponding in the cul-de-sac area. And the main reason that we are seeing ponding in this particular cul-de-sac is the poorly sloped waterway that it is supposed to exit at. It's at a pretty bad slope, about 1.8%. and also the design of that particular water exit, it just is not able to handle very much water. The second problem we see at the site is erosion. Now, once the water does reach the end of the waterway, it travels down a greenbelt area until it enters the stream. Now, in the greenbelt area, there are several obstructions that are in the path of the water. And once the water reaches there, it just erodes around it. And you can see that picture of the stump. That's in the middle of the waterway. The water has just continued to make that deeper and wider. And so there's several of these sites located at Site A. So from the map area, this is an image that we developed. It shows the directions of the water flow at different locations in the neighborhood. And so we were able to use topographical maps and ground proofing to go out and just see what direction the water would go at certain streets. So this was really valuable to us because it helped us to determine how much of our areas could be subdivided into subreaches. And so the area in purple, around right there, is the area at problem site A. And so there's a pretty good amount of area that's contributing to this watershed. And so we were able to use this information to develop solutions. Now, the original design for problem site A has a very small drain, and it leads into a 4-inch diameter pipe. This pipe is extremely undersized for the amount of water that comes to that cul-de-sac. And so on top of that, the pipe is broken. Yeah. So the broken pipe area has a large eroded spot around it. This is bad. For one thing, the erosion is continuing to expand. We started in August, and we can go back and there's an obvious difference in how much area has been eroded at this spot. And on top of this, it's a common entry point to the greenbelt area where there's a pool and playground. And so this is definitely a high priority site for us. Another problem at the design of this outlet is the fact that the soil and the grass level is raised above where the water can actually drain into it. And so what will happen is that it'll build up, it'll go through that pipe, but not fast enough. And so it'll eventually back up into the cul-de-sac, and it's potentially causing problems in a driveway at a residence home there. So when we were thinking about solutions to this particular site, we knew that we had to prioritize getting the slope of that waterway corrected. Like I said, right now, it's about 1.8%. So for our final design, we wanted to change that to a 4% slope. Currently, the 1.8% slope travels to about 120 feet in length. At that point, there's a hill at almost 10%, and the hill helps to guide the water to where it needs to go, eventually to the stream. So for our final design, the 4% slope will continue until about 150 feet, and then it will exit near the end of the hill and be able to travel to the stream much more efficiently without causing ponding in the cul-de-sac. These are images that we were able to develop using AutoCAD software. We took measurements from these sites and were able to input that data into AutoCAD. And so we took the current swale and we were able to use our designs and edit that in the AutoCAD to make the final design of that swale that you see. So a little bit about the mathematics and the hydrology behind this. We first had to determine our time of concentration of the sub-watershed, that purple area. The time of concentration is the amount of time it takes from the water at the very edge of that watershed to reach the exit point. There was a couple of assumptions we had to make when finding our time of concentration. And the first thing we had to consider is the fact that the path of the water is not a straight line. A lot of times the path of water is determined by the slope of the land. So if you have just an open field or an area like that, many times the path of the water is linear. However, with Parkview Estates, the design of the stormwater system is through the streets. And so there's no underground piping system that the water is directed to. It's actually all on the surface. And so the houses and the yards and the driveway, it's designed to put all of the water into the street, and the street is the conveyance system. And so we had to take the length of the furthest street to the outlet in order to get our time of concentration. And this was just one of the assumptions we had to make because it was an urbanized area. So once we found our time of concentration, we decided to go ahead and find our rainfall intensity for that area. Rainfall intensity is just the amount of water that comes down at a certain time rate. And so we based this intensity on a 100-year, 24-hour storm. This was chosen because the city of Stillwater designs their stormwater systems with a 100-year, 24-hour storm, which is basically a storm that you would expect to see every 100 years. It's very large. And so we wanted to see if we could match this design parameter with our own project. So we determined our time of concentration. We went to the ODOT roadway and drainage manual. We're able to find the rainfall intensity from an IDF curve there. Once we found that, we wanted to determine what our maximum flow at problem site A would be. And so that's the peak flow, which we use the rational method for that. That's the second equation you see there. And finally, to determine if our channel was capable of handling the peak flow, we applied Manning's equation to the swale, which is that bottom equation. So the peak flow we determined was about 35 cubic feet per second of water. As you can see, we multiplied our intensity, 10.5 inches per hour, multiplied that by the area of the contributing watershed, 8.24 acres, and then that 0.4 is our runoff coefficient. That basically indicates that asphalt is the avenue of the water to get to the outlet point. So yeah, it's hard to imagine 35 cubic feet of anything coming at you. So we were not really sure if our design would be able to handle that much water. You know, maybe we might have had to downgrade to a 50-year storm or a 25-year storm. So we applied Manning's equation to our swale, and we cut it up into 14 different cross sections. And so we applied Manning's equation at each cross section, we summed them and took the average. And what we found is that if we take just the added swale that we want to put in, it will handle about 23.8 cubic feet per second of water. But the area around it, from house to house, including all the green space that it has to go to, that can handle 42.7 cubic feet per second of water. And so after these numbers, we were quite confident that, yeah, the swale is capable of handling a 100-year storm, given that condition. Here's a top view of the current swale compared to the new swale. The swale that we want to be constructed in this area, we want it to be parabolic in shape and really very smooth with the existing condition of the whale. It'll be about 12 feet wide, roughly 150 feet long at a 4% slope. After construction is completed, there will be about 6,000 cubic feet of soil removed from that site. And then there will be about 350 square feet of sod cover to place after that. The sod cover is extremely important because we really need to establish vegetation at this site in order for it to be successful. If there's no healthy vegetation, it will erode just like any other site. And this will also help to slow the water velocity as well if there's healthy Bermuda sod growing there at a fairly decent height. Here's another image of the swale. And as far as the greenbelt area goes, all of the obstructions that are in the waterway, they must be removed. That pipe must be removed, the stump and the other rocks in that area have to be taken away and regraded to the shape of the swale that's surrounding that area. So after the regrading, again, we need to put Bermuda sod down at those sites and allow the vegetation to grow. And so after all these changes have been made, we're pretty confident that this area won't be experiencing ponding in the cul-de-sac or erosion along the greenbelt area.
Okay, moving on to the final design, Site B. This is one of our high priority sites, one of the ones that we've mainly been focusing on. As you can see, there's severe erosion on the both left and right side of the banks. This is caused by large volumes of stormwater coming into the stream, hitting these bare banks that have no vegetation on them and eroding the soil. What this site is experiencing is severe head cutting. This is when, and undercutting, and this is the term that's used when erosion is affecting the bottom of the bank, and you're getting almost like a big U shape, and then the tops will start to fall. So far, when we started in August, this site has increased probably about 2-3 feet in width. The erosion is getting worse and worse. The pool there is about 6.5 feet deep, and the width of that stream, width of the hole right now is 13 feet wide. So the location of this site is kind of southeast of North Williamsport. This is a little out of the way. There are other sections that are definitely more noticeable in the Greenbelt area, but this design can be applied to those as well. Some hydraulic facts about the site. Since it was a stream, we were able to use stream stats and get a mean annual precipitation of around 37 inches per year. The drainage area is over 100 acres, draining all into this stream when it rains. The average daily flow is very low, and that's because the stream is ephemeral and it only fills up when it rains. And so after it stops raining, the flow is down to a trickle. The way we approach this problem, and since it is ephemeral, is to look at it as a gully more than a flowing stream. Some simple design went into this as we would measure the depths of the stream and the heights of the banks and take 2/3 of that value and then go horizontally outwards, and that's when you would begin to excavate the banks and make them into a more stable 45-degree slope. This will make a more healthy system for the stream and will allow vegetation to take hold. After the banks have been graded, Bermuda sod will be planted to help with erosion, and the big thing is the water that is standing there. Like I said, this pool is really deep. It all needs to be drained and filled with soil, compacted, and then covered with riprap. Now, riprap are large stones that are put in place of the stream along the banks, along the stream bed, that help to reduce erosion. But when the water comes in, high velocities, large volumes, it has a lot of energy behind it. And this riprap will slow that energy and decrease erosion. Here's an example of the riprap. This is not us, this is a picture online, but it does has a great image of what it would look like. Once the water is drained, some soil put in and compacted, then you will begin to place large stones along the bottom of the bank and then work your way up with smaller stones until the top. So all of the soils is basically covered, and therefore it'll decrease the chances of erosion and the whole soil washing away. Here are diagrams of the proposed design. This is to help you picture it. Now, this is a perpendicular cross section. You'll be looking at the stream head on with it cut in half. The slope, the bank on the left is a little bit not as tall and steep as the bank on the right, but a 6.5 foot depth of water in this small gully is pretty severe. As you can see, the stones on the bottom, that will be where the riprap is placed. Here is another one to help you picture it. The water will be flowing this way and leaving this way. This is a horizontal cross section. You can see, again, the soil will be excavated to make a 45-degree bank slope, and then the riprap will be added along that inlet. So when the stormwater comes in, it'll hit that water and dissipate the energy, reducing erosion. Here is what the aerial photo will look like. Starting on the left side, working our way right, you will see the green area. That is the Bermuda grass that is to be added on the 45-degree slopes. We have smaller stones working our way through the middle toward the larger stones. And this whole place will be lined with riprap after excavation. And you can see how wide it is now. It will be wider afterwards, but it will be a stable and healthy environment. So this is where it comes down to cost. For the entire project, both site A and B, we're looking at around $6,500 to $7,100. After contacting previous excavation companies, we were informed that the site is very small. and that they wouldn't consider working on this. They referred landscapers. So we took it upon ourselves to just go ahead and do some of the landscaping calculations. Using local price estimates from, say, United Rental, $600 per week for a skid steer and trailer. Now you're looking probably a little over a week's worth of work with a landscaping company. That'd probably be about $4,000 to $5,000 a number. The turf for 450 square feet. This would be to cover Site A and Site B, around $1,000. The riprap just for Site B would be around $500.
All right, and then talking about some of those future expansions that could be added to some of these sites. We still would really like to see some LID implemented in this area. The main issue is the soils are so full of clay that the water can't really infiltrate very well. So any LID we implemented would have to be enhanced. So starting here with our enhanced bioswale, we could add this to the current swale that's already there. We would just have to go through and take out a layer of topsoil and replace that with a more permeable soil, such as a sand, some, asphalt aggregate included possibly in that area to help infiltrate the water, so we're not pushing as much water straight through that area and getting some of it down into the soil and reducing kind of the surface runoff, as well as permeable pavement. We're in a neighborhood, so obviously there's going to be a ton of concrete in the area. All of that being an impermeable surface, you're just pushing all of that water to the green space. Permeable pavement could be a very great application in helping to reduce the surface runoff as well, allowing the water to infiltrate into potentially, like in this diagram, an under drain where it didn't have to run across the surface and cause as much erosion. Another LID practice we would potentially like to see implemented would be a bioretention cell. So here, this top picture is at the very bottom of the hill at East Marie, kind of a meeting point for several flows. And then over in this right-hand picture is down before the water enters the stream. At the bottom of East Marie, we believe that anywhere upstream from this area would be a great place for a bioretention cell. You have several different inlet flows coming together. It'd be a great place to kind of slow the water down, allow it to infiltrate. This would also improve the water quality reaching the stream, helping to kind of clean out the soils, or clean out the contaminants from the soil before it gets to the water. Moving into Site B, as you can see in these pictures here, there are several places where the banks are still pretty sheer. As a future expansion, we'd like to see the entire length of the stream reshaped to kind of get that nice 45-degree angle to reduce kind of the head cutting and undercutting erosions, as well as the riparian zone. In the time that we've been out there, we have noticed a very concerted effort from the homeowners in kind of leaving a no-mow zone on either side of the banks of the stream, and we'd like to see that continue. The riparian zone really helps kind of hold in the banks and slow down the water before it gets to the stream. It has to go through taller grass with longer roots before it can kind of tear up the soils around there. So that riparian zone is very important in helping keep the stream together. A few other things that could be implemented within the stream itself. One rock dams, that would be like one rock tall. Could help if there's a place where the water is moving too fast and causing erosion. This would be a good place to kind of break up that flow and kind of cut down on the energy that the water is carrying, having to go through these rocks. As well as log and fabric stepfalls, areas where the water is kind of cascading down and causing erosion into a pool. This log and fabric stepfall would give the water would have to hit the logs before it could hit the soil, potentially, breaking up the energy and reducing the erosion in those areas. Moving into Site C, this was an area that we decided to kind of leave out for cost benefit. That being said, if they were to kind of address this area later on, we'd like to see larger riprap added. As you can see, because of this large outlet, some of this riprap has washed away, potentially because it was undersized. We'd like to see a little bit bigger, a little bit better riprap implemented in this area. And then the area, as well as sodded, we'd like to see more vegetation in this area. help hold the soils in so that it's not eroding away, as well as potential regrading. If you look downstream, it kind of bottlenecks in. We'd like the water to be allowed to spread out a little more so it's not hitting the stream with as much velocity, having to go through kind of a smaller inlet with the large amount of water that comes through this outlet. We'd like to just take a few seconds to say thank you to a few people. Dr. Weckler has been fantastic this year working with us, putting up with us, more like, but. And then Dr. Vogel, he's been very helpful. He's kind of our specialist guy. Anytime we have a very particular question we need, Dr. Vogel is always there for us. And then of course the Parkview Estates Homeowners Association and residents, many of which are here today, have been very hospitable to us, been very helpful with us, anything we needed while we were there or anything we've had. They've been really great for us. And then questions?
Let's get
Where to start?
I have a question. I think in site B, we were talking about putting the riprap into that one section and bringing in soil. Would you recommend using, we know that clay is horrible for that area already. Would you recommend bringing in a different type of soil to go with the riprap? Or would you, or using the existing clay that's there and maybe taking it out of other areas using that?
What would probably happen is the soil that was excavated at Site A, or even the soil around the banks, would definitely just be reused again.
Okay.
To save on cost. Yes, Dr. Vogel.
Question on that site right there, so as that's rebuilt, you're gonna still have a little pool after the storm. So did you guys think about, is that gonna be an issue if you have water sitting in that gully area for an extended period of time after the storm? Obviously there is now, but even after the fix, you'll still have that there.
It won't be as severe. The pool will be very small. The elevation on the inlet side where the water is coming in will be higher, built up higher than the when leaving the leaving side outlet of the rock. So water will be there. It won't be a huge, dangerous pool as it is now. It'll be a rock pool, and the water will either evaporate or trickle down.
Did I see correctly that the depth on it is 6 feet, that hole that you measured?
Yes, I tried to do some surveying in there. It's pretty difficult.
The current depth is 6 feet.
What
We're,
safety features you have for kids that are playing in there with the ball?
Currently, there are none.
I know.
There.
The current hole is 6 feet, but the new design one will be raised above that. It won't be that deep.
Yes, sorry. Okay.
One question, riprap size, did you do any calculations on velocity and what kind of riprap, or what size of riprap you need for the various sizes that you were referencing?
No calculations of riprap. Just the basis of larger stone, medium-sized stone, and smaller stone.
There should be some guidelines that we took from a study, I think from the NRCS, about riprap sizing for this stream. Should be in the report.
Did you talk to the homeowner association about their mowing equipment and what slopes that they can use that are best for their mowing equipment? I think you're showing one slopes, and did you talk to them at all about that?
No, not the maintenance. The only part of we talked to the homeowner association and maintenance landscaping is the riparian zone, which I say is working great. Since August, it's been dead grass for quite a while during the winter season, but now that the riparian vegetation is coming up, we're already starting to see a lot of vegetation come back on bare spots that we didn't think that would happen, and it's working great so far.
We do know that lawnmowers, their maximum slope that they really should be able to handle is about 5 to 1, horizontal to vertical. And the banks of the stream will be about 45 degrees, but there shouldn't be any mowers at that particular, at the bank of the slope. If they wanted to weed eat occasionally to kind of help the vegetation not get too out of control, that'd be fine, but mowing probably won't be happening.
Yes, ma'am.
You talked about the max channel flow on the site A, I believe, swale. And you mentioned that you averaged the flows through that, you averaged all the flows throughout those cross sections. Why did you use the average and not the minimum or most limiting flow to calculate your maximum flow?
Well, I think in that case, it was just be able to give, there's a high range that we go to, there's a low range that we go to, and the average, I just felt comfortable putting it in the middle.
I have a question. The vegetation that we are now letting grow on the sides of the banks, how high can that, I mean, if we were to weed eat like the tops of it off so that it doesn't really become, how high should it be if, it's tall?
As long as it's not mowed directly down, as long as I would say about a foot. Maybe. You want these plants and the vegetation around the street to be healthy. And the long roots holding all the soil together. That's the main part.
Right.
So bare grass that's been cut is not like that. Definitely.
I think on side A, you had some numbers of 5,000 to 6,000 cubic feet of soil being moved. Where is that being moved to? Is that being used at some other site?
Some would most likely be excavated and used at the site B for packing down that large hole, but the rest would just be.
We'd use the rest to fill in any of these holes, like the stump hole would be filled with this dirt. After the pipe was removed, that would be filled back in, because I'm not sure the pipe's necessarily part of our swale. Just those kind of areas. Any
Much of
areas
it
where
will
there's
be,
current-
much of it will need to be removed off-site.
Paul, since we have a lot of customers here, Mount Stillwater out there, kind of by Walmart on 6th Street, back over there. When we did the stream restoration site, they moved a lot of the soil over there, and that developer will take soil from other folks.
Will he supply the dump truck? Something to add to your budget, dump truck.
Thank you. Anything else? Anyone?
Any other questions for this group? If not, well,
Did the city indicate any interest in participating in the project?
Yeah, there's a possibility of that. We did hear that there's a possibility of that. The homeowner association will have to coordinate with Charter Labs and other city planners. And yeah, it's possible.
Maybe I missed it, but what was your plan for the exposed sewer manhole?
We currently don't have a plan for it. It was kind of a looping point to hopefully get the City of Stillwater involved to help with a potential plan for that. That being their property, I guess.
Charlotte, can you answer
What I would say is that the homeowners association in the city will meet, and we would just schedule a date, so.
I need to call them on.
okay, let's give this group a round of applause.